Module 3, Session 3. Session 3 will cover Learning Outcome 4.3.3, Part 1, Drawing Tree Diagrams. Learning Outcome 4.3.3, Part 1, Drawing Tree Diagrams. Tree diagrams are a very useful tool for counting the outcomes in multi-step experiments. We call them tree diagrams because they are shaped like branches of a tree. They are particularly useful for working out dependent events as they help us to visualize the changes in the outcomes. Lecturers we interviewed said that drawing tree diagrams represents a real area of difficulty for students. Let's look at an example of tossing a coin twice. Let's start with the first toss. Here is the first stage. The number of branches at each stage represents the number of possible outcomes. With the first toss, there are two branches, heads and tails. The probability of each branch is written on the branch. The outcome is written at the end of the branch as H and T. The sum of both branches in toss 1 should add up to 1. What happens if we toss the coin again? Now we need to add two branches for each of the branches from the first stage, one for heads and one for tails. The probability of getting heads and tails for each throw is still 1/2, so we write a half along each branch as before. The sum of each set of branches in toss 2 adds up to 1. The possible outcomes are written at the ends of the branches, and they are HH for the first branch, HT for the second branch, TH for the third branch, and TT for the fourth branch. In this way, the tree diagram illustrates all the possible outcomes, also called the sample space, for two coin tosses. This list of possible outcomes gives the tree diagram its power, as it makes it almost impossible to miss any combination. Once we have the sample space, we can choose the ones we are interested in. Now we can use the tree diagram to compute the probability of getting, for example, heads for both tosses. Only one branch along the tree gives heads then heads again, which is HH, as shown here. We multiply the probabilities along the branches. A half times a half is a quarter, so the probability of getting HH is a quarter, or 25%. Now, perhaps we want to know what the probability is of getting a different result for each throw. In other words, we are interested in HT or TH. So we are now looking at two branches on our tree diagram as shown here. Again, we multiply the probabilities along the branches. Each branch has a probability of a quarter. But now we are interested in the probability of getting HT or TH, which is two branches. So we add the two probabilities together. A quarter plus a quarter is a half. So the probability of getting two different results in two throws is 1/2, or 50%. Remember, we multiply probabilities along the branches, and we add probabilities down the columns. Be careful! The probabilities are not always equal along all branches. For example, if you have different numbers of objects. Also note that if you have a dependent probability situation where you withdraw without replacement, as in our example with black, yellow, and red balls, the probabilities on the branches change after the first draw. Let's see how a lecturer uses tree diagrams to solve a probability problem.
If a coin is tossed 3 times, use a tree diagram to find what the probability is for getting 3 tails, 2 heads and 1 tail, 2 tails and 1 head. We're going to have to use a tree diagram for that. So this is toss number 1. For toss number 1, you get a head as well as you get the tail. Once you've done the first toss, you do the second toss. Which gives you again a head, a tail, as well as a head and a tail. Now what is this? This is toss number 2. So this is the second toss. You flip your coin again for the third time. So what does it mean? It means the same thing. In every toss, there's an outcome of a head and a tail. Outcome of a head and a tail. This is the tree diagram representing that. So I've used these different colors for the purpose of understanding and demonstration. And my answers, we will put them here. Number A, B, and C. Now, we are focused here. When you are focused here, you will count how many heads are here. There are 3 heads here. This outcome, this 3, gives you a branch of 3 heads. And then if you follow the same branch now, you follow this branch, take it from here. There we go, there we go, there we go. So we've got 1, 2, 3. So which gives you head, head, tail. Then you follow this branch, 1, 2, 3, which gives you head in the first toss, tail in the second toss, head. Then continues. 1, 2, 3, which gives you the same applies here. Again, it's your tails, followed by your head, followed by your tails. And then, so which is tail, tail, head. And lastly, now once you have your tree diagram, you answer your questions. What is the probability of getting 3 tails? You look where there are 3 tails here, following each other. It's this one. So, how many outcomes are here? 1, 2, 3, 4, 5, 6, 7, 8. So, which means that there's only one outcome out of 8 chances. Out of 8 chances, there's only one outcome that gave you 3 tails. So, which is going to be 1 over 8, which should give you 1 divided by 8. Our answer is going to be to 3 decimal places, 0.125. That's number A. Number B, you're getting 2 heads and 1 tail. 2 heads, 1, 2, 3. That's the only outcome. Those are the only outcomes with 2 heads and 1 tail. This one, this one, this one. So which means it's 3 over 8, which gives you and lastly, probability of getting 2 tails and 1 head. Now you're looking at 2 tails. 2 tails and 1 head. 2 tails, I see you here. 2 tails, I also see you here. And lastly here. So which then makes also 3 over 8, which is equal to 0.3. 3, 7, 5.
Now, work in groups to do this activity on tree diagrams in probability. Here, a coin is tossed and a die is rolled. Let's watch a lecturer working through this problem.
Let us look at the following problem. A coin is tossed and a die is rolled. Now we begin by looking at the coin toss and we call this event 1. When a coin is tossed, there are two possible outcomes. You can either get a heads or a tails. As you can see, you can get one of the two possible outcomes, therefore the probability of getting either a heads or a tails is a half. Now when a die is tossed, there are 6 possible outcomes. You can get a 1, a 2, a 3, a 4, a 5, or a 6. So when you toss a coin and you obtain a head, there's a possibility of rolling a 1, a 2, a 3, a 4, a 5, or a 6. Similarly, when a tails is tossed, you can get a 1, a 2, 3, 4, 5, and 6. So the chance of rolling a 1 is a 1/6, and since the possible outcomes for each of the die rolls are equally likely, therefore you'll obtain a 1/6 for each of the die rolls when you roll a head and when you roll a tails. Looking at the outcomes, we can see that there are 12 possible outcomes for this experiment. You can toss a head and get a 1. You can toss a head and get a 2. You can toss a head and get a 3. And this is the case for each die roll. This is similar for when you toss a tail and roll a 1, a 2, a 3, a 4, a 5, and a 6. Now, the probability of any path in order to obtain the probability of any path on the diagram, we simply multiply the probabilities on the branches, starting at the origin of the branch and tracing the path along the branch to the last part of the branch. For example, if we wanted to obtain the probability of tossing a head and rolling a 1, we would take the first part of the branch, which is a half, multiplied by the second part of the branch, which is a 1/6. And we would get 1/12. We mentioned earlier that each of the 12 possible outcomes are equally likely. Therefore, the probability of obtaining one of the 12 possible outcomes are all 1/12. this was an error and it's supposed to actually be H5. So the probability of tossing a head and rolling a 5 on the die. The probability of obtaining a heads and rolling 1 to 6 on the die is similar for that as that of the heads case. We can verify this probability by the fact that if we take a half along the branch multiplied by a 6 along the subsequent branches, that for each of the outcomes we will get 1/12. Now looking at the second part of the question, it asks us to define the sample space. Now the sample space is simply all the possible outcomes from the experiment. In our case, the outcomes involve tossing a head or a tail and rolling a 1. And as you can see, this column indicates the possible outcomes, which in turn form our sample space. So this is question 2. And we list all the possible outcomes in our sample space. So that is the tree diagram completed, and along that we've indicated what our sample space for the experiment is. The next part of the question asks us to find out the probability of getting a heads and a 2. To determine the probability of 2 dependent events occurring, we use the following formula. In our case, the probability of getting a heads and a 2 fits into the formula in the following manner. From the diagram, we can see that the probability of getting a heads is a half. While the probability of getting a 6, of rolling a 6, is a 1/6. Therefore, we take a half multiplied by a 1/6 and we get 1/12. The next part of the question asks us to determine the probability of getting a heads or a 2. To determine the probability of 2 mutually exclusive events occurring, we use the following formula. In our case, the probability of getting a heads or a 2 is the following. we obtain the probabilities for each of these events from our tree diagram. So the probability of tossing a heads is a half. The probability of tossing a heads and rolling a 2 is a sixth. And lastly, the probability of tossing a tails and rolling a 2 is also a sixth. If we add each of the individual probabilities, we get a final answer of 5/6. The next part of the question asks us to calculate the probability of getting a heads and an even number. Okay, so we're going to look at the top section of the tree diagram. And we are looking only at even numbers. So 2, 4, and 6. So once again, we are looking at obtaining the probability of tossing a heads and rolling a 2, the probability of tossing a heads and rolling a 4, and lastly, the probability of tossing a heads and rolling a 6. If we go back to the tree diagram, we can see that the probability for each of these outcomes is 1/12. Therefore, we simply add the probabilities for each of the individual outcomes. We simplify the equation and we get a final answer of 1/4. The last part of the question asks us to find the probability of obtaining a heads and a tails. This is an impossible event because we cannot toss a coin and simultaneously get a heads and a tails. Therefore, the probability of getting a heads and a tails is 0 and is termed an impossible event.
Here is another, more complex tree diagram activity using a deck of cards. Work in your groups to solve this problem. Do your students struggle with this type of activity? Think about how you can help them. Let's take a look at the solution to this activity.
Let us look at the following question. 2 cards are drawn one after the other from a deck of cards containing 52 cards. The jokers from the deck have been removed. The card drawn in the first round is not put back into the deck before the second card is drawn. Now, the first part of the question asks us to draw a tree diagram to show the possible outcomes with regards to drawing king versus drawing other cards. Now, it's important to note that the tree diagram that is going to be drawn is going to be done so without replacement. This is because the second part of the question states that the second card will be drawn without the first card being put back into the deck. Now, as indicated, the deck consists of 52 cards. There are 4 kings in a deck of cards. Okay. Therefore, the probability of drawing a king from the deck is 4 over 52. We have 48 cards remaining after we have excluded the kings from the deck. Therefore, the probability of obtaining or drawing any other card besides a king is 48 over 52. Now this is the first event, which is drawing the first card from the deck. The second event looks at drawing a second card without replacing the first card. Since we are not replacing the first card, we are only left with 51 cards in the deck. So there is a possibility that we can draw a king from the deck, or we can draw any other card that is not a king. Similarly, we can draw a king and a card that is not a king in event 2 when we have drawn another card in event 1. Now let's look at the first branch. Given the fact that we have already drawn 1 king from the deck, we are only left with 3 kings in the deck. Therefore, the probability of drawing a king in the second event is 3 over 51. Looking at the first branch again, given the fact that we have drawn 1 king from the deck, therefore the probability of drawing another card in the second event is 48 over 51. Now let's look at the second branch, which is here. Given the fact that a card besides a king was drawn in the first event, there are still 4 kings left in the deck. Therefore, the probability of drawing a king in the second event is 4 over 51. Looking at the second branch again, we've seen that we have drawn a card that is not a king, and this leaves us with 47 other cards that are not kings. Therefore, the probability of drawing a card that is not a king in the second event is 47 divided by 51. From the diagram, we can see that there are 4 possible outcomes. We can draw a king and a king and another card. We can draw another card and a king. And lastly, we can draw another card and another card in the second event. In order to find the probability of each outcome, once again, we simply multiply the probabilities on each branch in the diagram, starting from the origin of the diagram and tracing the path along the branches all the way to the last branch of the diagram. The probability of obtaining a king in the first event and second event is equal to 4 over 52 multiplied by 3 over 51. And we are simply getting the values as mentioned from the branches. This can be simplified further. The probability of getting a king in the first event and another card in the second event is 4 over 52 multiplied by 48 over 51. And this is simplified to 16 over 221. The probability of obtaining another card in the first event and a king in the second event is equal to 48 divided by 52 multiplied by 4 over 51. And this can be simplified to 16 over 221. Looking at the last branch and the last event, the probability of obtaining another card in the first event and another card in the second event is equal to 48 divided by 52 multiplied by 47 over 51. And this gives us a final probability of 188 over 221. So as you can see, once again, that the probabilities for each of the outcomes is obtained by looking at the branches for each of the individual events and multiplying those probabilities together. The next part of the question asks us to determine the probability of drawing two kings. This involves drawing a king in the first event and drawing a king in the second event. From our tree diagram, we can see that the probability of drawing a king in the first event and second event is given by the following formula. Therefore, we can write it as such. Remember, we're obtaining the probabilities for each of the individual events from the tree diagram. So the probability of obtaining the first king is, we get it from this branch. And the probability of obtaining the second king is obtained from this branch over here. And we get a final answer of 1 over 221. And this is verified in the table where we calculated the probability of achieving the first outcome. The second part of the question asks us the probability of obtaining no kings. This involves drawing no king in the first event and in the second event. We simply find the probability, the branch of the tree diagram where we do not want to draw a king in the first and in the second event. And this is indicated by this outcome over here. We multiply the result because we are determining the probability of two independent events. Okay, so and we obtain a final answer of 188 over 221. Another way of solving this problem is by looking at it as a complementary event. To determine the probability of a complementary event occurring, we use the following formula. Now, as you can see, there are 4 possible outcomes. Obtaining a king and a king, or a king and another card, or another card and a king is the complement of obtaining no kings. Therefore, the formula becomes we obtain the probabilities once again from the branches in the tree diagram. We simplify the equation and we get an answer of 188 over 221. And as you can see, that the answer for the first method and the answer for the second method correspond. The next question asks us to determine the probability of drawing one king only. This is equal to drawing a king in event 1 or drawing a king in event 2. If we go to the tree diagram, we see that the probability of drawing a king in either event 1 or event 2 is 16 over 221. Since these events are mutually exclusive, we add the probabilities of each individual probability to obtain a final value. And we obtain a final value of 32 over 221. The last question asks us the probability of drawing at least one king. If we look at the outcome column of our probability tree, we see that outcome 1, 2, and 3 gives us a probability of obtaining at least one king. Since these events are mutually exclusive, we add the probabilities of each of the individual events. We simply substitute in the probabilities from the tree diagram into our formula. And we obtain a final answer of 33 over 221. Therefore, the probability of drawing at least one king is 33 over 221.